code. As I said, it's a file about this software. So I talked about the sample of input and output file, and this is the executed file for the code. I think you should be able to run it at least on Windows. I'm not sure about the Mac. I couldn't run it on my Mac, but on all Windows universities, the PCs or laptops, you can run it. So when you run it, it's just something like this. So just ask you for input file, the name. So for example, I have an input file. You need to use .text. So I assume that you already created an input file. So I want to show you how to run this code. So input file, assume that this is the name of the input file that I have, input.text. Then it asks you for an output file that you don't need to create it in advance. You can just use, for example, test. It's a file that is finally created by the code, so it basically restore all the information. And then when you hit the So it will start calculating, so number of cycles, track length, and different segments that you define. I will show you how to prepare this input file. And whenever it's done, basically it will start calculating, and in the middle, whenever you want to stop it, it's just Ctrl+C, you can stop the code. Anyway, so running the code is just in input and out. Yes?
Is it looking for the input.txt file in that folder specifically?
Yes, I use this one to run the test. You have the same file as an example. This is not what you basically use for your final, problem, but this is an example. I will go over the input file just. So the input file that I put for you, you can basically run it. But based on that, you create your own input file based on this load calculator, based on the specimen that you have, the configuration of the crack and size of the crack. I will go over it. Just wanted to tell you that running the code is very simple. Just input and output file and done. So this is the description of the problem for each of them. So we have two types of a specimen. This is a specimen 1, and this is a specimen 2. For specimen 1, we have two types of crack configuration. One is basically a crack in the middle of the thickness. The other one is the true crack. And here we have three configurations for the crack. Crack can be in this side or in this edge or can be corner. So based on the student ID, you get, for example, specimen 2 configuration 3. So specimen 2 configuration 3. So that would be your case. And you get the size for A and C, which is basically the size of the crack. Is it clear? That's fine if you want to work together to learn about this code, but most likely for each of you would be an individual. Specimen type and crack size. What else you need as input? You need property of material. The most important property of material you need is a table for crack growth. So delta K effective versus number of cycles, the crack growth rate. So these are also input to the file that I'll show you. And some other information about the, for example, fracture toughness is KF here, yield and ultimate and normal. For each of these specimens, you see a table and a graph, which is the experimental result. And finally, you compare your predicted result with the core result. So this is for specimen 1, the SN maximum stress versus number of cycles to failure, and our ratio was 0.1. And this is for specimen 2. Minimum stress, maximum stress, and number of cycles to failure. So what you need to report or send is basically, first of all, refer to that input calculator and find your specimen type and track configuration. Just the input and output file of your FastRAN code, that's what I need. Just put the predicted life for the stress level that you defined in a table. So the stress level doesn't necessarily need to be the stress level that you see from the experiment. Just different levels that cover. For example, here you see the test are from 50 to 300. So any stress level that covers this range, that works as input stress for your code. You can just use the same stress levels that you see here. Or any other stress. For example, it doesn't matter if here is 300, 270, 250, you use, for example, 310, 260, doesn't matter. As long as you cover this range that you see for experimental results, that will be fine. And finally, you plug an SN care for your predicted care and experimental data, something like this. So these are assuming that the experimental data that I given you, and based on the life that you get from the software, you create a care, you fit a care on that, and you compare the experimental result with that predicted care. So report is not something, just a table and a graph. That's what I need, plus you need an output. Nothing more, just table, graph, input and output. Yes.
For the input and output file, are we putting those like separate from, because it's a separate file, are we just submitting all of them? Or do you want us to like upload or input?
So it will be just one input file and one output file. Two text file, plus a Word document or whatever containing a table and a graph. So about the input file. So first of all, you need to kind of look at that, the user guide that I gave you. So all the information about creating that input file is there, but very quickly I go over the input file, the example that I gave you. So it's a text file like this. So for this different stress level, you can just create one input file. You don't need to change your input file. So for example, you see this input file has a name for A, B, and these are basically repeating the same test for just different stress levels. But anyway, so there is a Word file that I copy paste just the same input file in the Word for you. So this number that you see, 5, 4, 5, 6, 7, whatever you see here, is basically the number that you see in the user guide. So for example, number 4 is material properties. So yield stress, ultimate, Young modulus. So these are the information that defined as section 4, which would be corresponding to this part of your input file. So those are that I highlighted in red is the most essential one that you need to change in your input file. The rest of them, most of the cases, you don't need to definitely change. First of all, if you don't know, for example, this one, it should be 0 or not, and you don't have any information about that, and you read the user manual, just leave it as is. But most likely, the red ones are those that you need to change based on your specimen and track. So for example, you already in that table have for material property. So you have the yield, ultimate, and Young modulus. So yield, ultimate, and Young modulus would be these two. And if you refer to the material tensor properties, number 4 is read, yield, ultimate, and Young modulus. And so based on that, you can find what are each of these. So most of the case, you don't need to change them. But this point 2 is, if you look at the user manual, it would be this alpha, which yours is 1.65. So then these reds are basically your table that I already given you. So you need to replace it just with this number. So delta K versus crack propagation rate. So you put that values here. This number 9 is basically the number of the rows that you have. For example, here is 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 9. If yours is 7, just put this as 7. So for all of this, you can see the description in the user manual. It's just 3 pages. This is the information. Number 12 is the information about the size of your specimen, thickness, width, and the initial crack size. So for your specimen, whatever it is, so for example, in this case you have the width is, for example, in this case 10, and thickness is 5 millimeter. So this one is width, this one is the thickness in millimeters. And if you go to number 12 in your so number 12 in the user guide, you see it's read WT, and there is description for each of them. Read the description. So some specimen you may need to use just 1/2 width or the full width or thickness. So thickness, initial crack length, C and A different direction. So just use that example as a sample for yourself, and you can find this. If there are other values, for example, this one or this one, if you don't know what it is, just leave it at 0 or 1 or whatever is in that one. This is the final crack length that you define, and usually final crack length is the size of your sample. So for example, here you see the width, the thickness is 4 millimeter, and final length of sample is 4 millimeter. So again, if you go to number 14, final crack length, you just define them. The next one is your stress level that you define, which is 642 megapascal here. And instead of, so these two are for maximum stress and minimum stress. It's number 18. So it's referred to as a scale. And this so it works like this. Assume that, so what you need as an input is the minimum stress or maximum stress. For any fatigue calculation, we need the minimum stress and maximum. So the way that you put it in the software is basically assume that your maximum stress is 642. Here is megapascal. Instead of giving minimum stress as a value, it's just the R ratio. So what you see is minus 0.12 is basically the R ratio that you have. So if you multiply this with this one, you get the minimum stress. That's the way that you put maximum and minimum. So for your case, other than the material property, which is the same for both specimens, so from here to here will be same for both specimens. What you need to define is the width, thickness, initial crack size, and final length of the crack, and the stress level. So this is just one file for calculating the fatigue life for this stress level and those cracks. So you can have multiple of these in a single input file. So if I open this input file, so you see A is start from here to here for this stress level. But after that, you can create another one, for example, B is just copy paste of the same thing, but I use a different stress level. So you can put all of this calculation, for example, for 8 stress level in a single input file, and basically the code solve it just right after each other and give you all the number of cycles to take. So you can run just a single input file from here to here for one stress level or for a specific condition. And again, for another stress level, for example 500, you can run another one separately. But usually put all of these, I put all of them in one file. So it's A, B, C, you see up to here, it's almost 9 different stress levels. And when you run the code, so right now it's just running the A is done, its second part is B is running. So whenever it reaches to failure, it automatically go to the next level. So it's C, so those the first two is already done. So as stress level was higher, so there are shorter number of cycles to fail. So it's solved it cycle by cycle. So while this one is running, so I want to show you how much does it take. It's just maybe 10 or 15 minutes. Usually, it depends on your stress level and number of cycles that you get. But in order of million cycles, it's just few minutes. So the code itself was developed in 1980 by Jim Newman at NASA Langley Research Center. And so there are some comparable codes by, different agencies. For example, Air Force has its own code. So FastRAM was developed at NASA at that time, and in many airplane design basically it was used. You can check it online. But for example, again, it's a very common type of fatigue calculation. There are comparable codes. For example, if you search AFGROW, so this one is very similar to FastRAM, but developed by Air Force. Some version of it would be basically free to download, and for some specific feature of that you need to pay. So that's one of the codes, very similar to that. There is another one, NASGROW. So this is also fatigue life prediction and characteristics development. They may have more modules than FastRAM, but very similar, very common. I mean, in aerospace industry, these are the code. These three are the codes that they use. I know Dan talked about the ENCODE, but that's more, for automotive industry, something like that. But these are the common codes for aerospace industry. So it considers also crack closure that we talked about, and also plasticity at the tip of the crack, and it solved the crack loss equation cycle by cycle. Inside the code, you have some different configurations of a specimen and case solution for it. So you need to have case solution. Some of the typical cases, you can look at that user manual. For example, different type of a specimen, surface crack. So there are already case solution in there, and you just need to find which one is your case in your input file. Some of them are just specific to, for example, a structural panel for aircraft, something like that, like this one. You have, for example, a rivet series of tracks and holes. That's for that one. So, for example, this is the one type of a specimen. So it is for you to find which of these. So N type basically refers to the case solution that you need to use. So for your specimen and your track configuration, I basically leave it for you to find in the code which N type you need to use. So somewhere here, variable amplitude loading, there are many options, but you're using a portion of this code. So these are the different type of the loading and specimen type that you can have. So this number basically refers to different conditions. So for the input file that I gave you, so it was a surface crack under tension and bending. So it's 0. But it may not be the case for example, when you have the corner crack or when you have that bending. So you need to check these, and also there are some drawings to see which one is your case. So in this file, so it's in number 10. The first one is the N type, the specimen type. Second one is the load type. So line 10, these two. So it's 0 and 0. So if you look at that manual, so 0 is the surface crack under tension and bending. So when L type is equal to 0, it's just tension. So for surface crack under tension, N type is 0 and L type is 0. So you can need to read this description and look at these drawings to see which one is your specimen and track. Because, so for example, N type for the corner crack would be different than side crack, and also for these two. It's not that difficult to find. So I forgot to highlight this. There might be more, other thing that you need to change, but these are the main. Any questions so far?
Do we have a due date posted for this? Like,
Not yet, but I will. Any questions?
The accessory software is temporary or you not give it to us?
So I have the permission to share it with you, but it doesn't mean that you can publish paper using this software or do any industrial job, I think. It's up to you.
Not officially, but unofficially.
But it's not gonna expire. You can have it. I mean, if you want to run a business using this code, and it should be problem. But for the students, and I mean, educational purposes, I think that's fine. I have permission.
I think it's just for Infinite Blade, yeah? It's not for just for Infinite Blade. You can
So Infinity's usually case solution is very simple, like the one that you have. So the problem is actually case solution for different geometries when you have boundary conditions. So that's the point of such a scope. So majority of them, I mean, there are, for example, these are specifically for aerospace for airplanes when you have rivets on the big plate. So case solution development for these was difficult. And there should be more options, I mean, on FastRAM. This version doesn't include all of those different structural types. Real cases for aerospace and NASA. So there might be excluded. Because I know there's an online FastRAM tool that you can pay for that. And there might be more structural cases. But many of the laboratory specimens, and including a few of these structural, like, I mean, 5 or basically, the panel with rivets are included. But the majority of them that we see are just laboratory specific. It's a useful tool. So. For some of these, there might be more details, but if you learn to create one of these input files, for many other characterized cases, like as I said, NASPRO and AFPRO, so all of them are kind of the same procedures.
Do we have any variation in the decimal number of cycles and the actual number of cycles? when it comes to industry or layout or making the product or something.
Just a second. So maybe I put the due date for this in 2 or 3 weeks. So what was your question?
And do you have any variation in the code, number of cycles, variation of number of cycles? Do you put the number of cycles in the code as a baseline and replace the product?
So always the baseline is basically the experimental data that you get. For example, in this one, I already gave you the experimental data. So you usually compare your code with that. Mostly on laboratory specimens, but it depends on the application. Most of the application is still you need to verify with the experimental results.
So you just can't keep this as a baseline for every product. You have to test with experimental data.
So it's wide range of track size. So it means that when you get your predicted life may not be, perfectly fitted on the experimental data. It might be a little bit this side or the other side, depending on the size that you use. So this one is just an example. It doesn't mean yours should be that perfectly fit on the experimental data. That gives you an idea. It should be something like this. So just the output file. So it's something like this when you open it. So for all those initial conditions, 9 of them. So it's description that gave you the crack size. Cycle by cycle, it gives you the crack size in C direction and A direction for each of the cycles. So the cycles that you see in the report is not necessarily 1, 2, not from 1 to 100, 200, and 1000. And also the rate is basically the crack growth rate. So at the end of the number of cycles to failure, you see the total cycle. This is what you need to get from your output file to put in the table. So you define the stress level, and based on that stress level, it gives you the total cycle. So easier way is just to search the total cycle in your file. So 2, 3, 4, 5, depending on the number of stress level that you define, you can quickly find that. So that's the only thing that you need to get from the output file, just the total cycles, and just search. So here is just 1, 2, 3, 4, 5. Maybe I stop the code in the middle or something. So rest of it will be basically the description of what you inputted in the file. What you need is just the total size. Any question?
It's not much what I did about you. Just grab something from them. I will give you reference. Okay. Just trust me.
So if there isn't any question, I think you are done. Just one thing, in the Word file that I put you as information for the input file, I put 2 examples. So if you look at them, they are exactly the same, just the initial track size is different or the load. For your case, even these 2 would be the same because you have just one track size. And what you change in different section of the code is just the load.
I ain't going to fly. Don't worry about that. I got it. Alright. Just, you hear me? You're not just this. Full of reading. Don't go insane with that. Promise you. Don't.
If you are done for today, good luck.
I did. These lights.